Welcome to Daily Papers, the podcast where we break down the most interesting research papers so you don't have to. Today, we're diving into the world of large language models, or LLMs. You know, the AIs like ChatGPT, Claude, and Llama.
Right, and there are so many of them now. It feels like every big tech company has its own version. The common wisdom is that if you want a reliable answer, you can ask a few different AIs, and if they all agree, you're probably on the right track.
Exactly. It's like getting a second opinion from a doctor, or a third. You assume each opinion is independent. But what if it's not? What if all those doctors went to the same school, read the same textbook, and were taught by the same professor?
Their agreement wouldn't be as meaningful then. They might all be making the same mistake because they all have the same blind spot.
And that is precisely the question a new paper from researchers at Texas A&M University asks. How independent are large language models? They suspect that the AI world might be a bit of an echo chamber.
An AI echo chamber. I like that. So what's the worry here? The paper points out that many of these supposedly diverse models are built using the same public data from the internet, similar training techniques, and sometimes one AI is even used to train another.
This creates what the authors call behavioral entanglement. It's a fantastic term. It means that even though the models have different names and come from different companies, they might be secretly linked, sharing hidden biases and reasoning patterns.
And this is a huge problem for systems that rely on multiple AIs. The big example they use is something called LLM as a judge. That's where you use a powerful AI, say GPT-5, to evaluate the answers of another AI.
The assumption is that the judge is an impartial, independent referee. But if the judge and the student AI are entangled, the judge might be biased. It might look at an answer from its entangled buddy, recognize a familiar reasoning style, even if the reasoning is wrong, and be more likely to approve it.
So instead of independent validation, you get a correlated failure. They both agree because they're both wrong in the same way. This makes our AI systems seem much more reliable than they actually are. So how do we even begin to detect this secret entanglement? It's not like you can just look inside their code.
You can't, and that's where the paper gets really clever. The researchers had a key insight. Don't look at when the AIs get things right. Most of the time, there's only one right answer, so of course they should agree. The real clues are in their failures.
So you do some detective work on their failures.
Exactly. They propose a statistical framework to analyze what they call the joint failure manifold. A bit of a mouthful, but the idea is simple. When AIs fail, they can fail in many different ways. If two models consistently fail in the exact same way, that's suspicious. It's evidence they're not thinking independently.
Okay, so how do they measure this?
They have a two-level approach. The first tool is called the Difficulty-Weighted Behavioral Entanglement Index, or BEI for short.
That sounds complicated.
The name is, but the idea isn't. The BEI score goes up whenever two models fail on the same question. But, and this is the key part, it gives a huge penalty when they both fail on an easy question.
Why an easy question?
Think about it this way. If two expert mathematicians both get a super hard calculus problem wrong, that's understandable. They might have failed for different, independent reasons. But if they both insist that 2 plus 2 equals 5, that's really weird. It's so unlikely to happen by chance that you'd suspect they cheated or shared a faulty calculator.
Got it. So synchronized failure on an easy task is a massive red flag for entanglement. That's the first level. What's the second?
The second level is even more specific. It's a metric called Cumulative Information Gain, or CIG. This one is for multiple choice questions. It doesn't just look at if two models failed, it looks at how they failed.
You mean which wrong answer they picked?
Precisely. Let's go back to our math experts. The question is, what is 2 plus 2? And the options are A, 4, B, 5, C, 3, and D, 22. If both experts not only get it wrong, but they both confidently choose answer B, 5, the evidence for entanglement becomes overwhelming. They didn't just fail, they failed in the exact same direction.
That makes a lot of sense. So the researchers unleashed these two metrics, the BEI and the CIG, on a whole ecosystem of AIs. What did they find?
They tested 18 different models from 6 major families, GPT, Llama, Claude, and others, and they found entanglement everywhere, not just within families, like different Llama models being very similar, which you might expect. They also found entanglement across different families.
So a model from one company could be entangled with a model from a completely different company.
Yes, and this had real consequences. They tested the LLM as a judge scenario and found a clear link. The stronger the entanglement between a judge AI and a student AI, the more likely the judge was to approve the student's wrong answers. The CIG metric, the one that looks at picking the same wrong answer, was especially good at predicting this bias.
Wow, so the entanglement isn't just a theoretical number, it leads to biased, overconfident evaluations. This feels like a big problem. Did the paper offer a solution?
They did. They proposed a practical fix. They call it the de-entangled verifier ensemble reweighting.
You're killing me with these names.
I know. Let's just call it the SMART committee method. The idea is, if you have a committee of AI judges voting on an answer, don't treat every vote equally. If you know from your BEI and CIG scores that 2 of the judges are heavily entangled, that they always think alike, you downweight their votes.
It's like saying, okay, you two only count as 1.5 votes because you're basically the same person.
Exactly that. You are actively penalizing the lack of diversity. And when they did this, the results were great. This SMART committee approach was up to 4.5% more accurate than a simple majority vote. In the world of AI performance, a 4.5% gain is a really big deal.
So the main takeaway is that we can't take AI diversity for granted. Just because we have a dozen different LLM brands doesn't mean we have a dozen independent minds. They might just be echoes of each other.
That's the perfect summary. Agreement between AIs doesn't automatically mean correctness. It could just be a shared blind spot. This paper gives us a statistical toolkit to look under the hood, identify these hidden connections, and build more robust and genuinely intelligent systems by correcting for that echo chamber effect.
It's a really important step towards making AI systems less gullible and more trustworthy. A fantastic paper.
It really is. That's all the time we have for today. Thanks for tuning in to Daily Papers.